FRQ 13, getting toward the end. Okay, so they give you a function f, and they describe the different parts. We have segments, and then each of these is a parabola. They give you the equation for the right one, and they give you the areas A and B. Okay, so 3 and 5. So first thing I did, once again, is I found all of these areas as quickly as I could. These are just triangles, so for instance, 1 times 3 divided by 2, 1.5, and so forth. For this one, the integral of f from 1 to 4, the work that they did later, this was a no calculator problem on a previous test. The work, they showed the work, you can do that by hand. You may forget that you have a calculator, but it's very quick. Enter this as y1 and use the integral function from 1 to 4 to find this area. Okay, so we've described that. Then they give you another function g, which is the area under that curve from -4 to x. Okay, so the first thing we have to do is find two values of g, and g of 0 would be the area from -4 to 0. From -4 to 0. So we just add these three areas up, and we can see their solution very quickly. 1.5, 3/2. Okay, no explanation needed. Okay, and g of 4 from -4 to 4. So from -4 all the way to 4. So we're going to add that 1.5 to these two areas right here and here. And this is where they showed all their work by hand, but we do just get 11. Okay, part B. The absolute minimum of g on this closed interval. Okay, so we're thinking about the slope of g. Okay, so we're looking for a minimum. G prime, if we look at g, if we derive g with respect to x, it's a fundamental theorem again, really expect that on the test. Okay, and so the derivative of that antiderivative is just f of x. So that's why they immediately write g prime is simply the y values of f. Okay, and so we look at the y values, and we're considering the entire curve here. Okay, so the minimum could occur at a place where x, or the y value of f equals 0. And we have different places here, which is actually an endpoint of the domain. Another one here, there, and there. But think about a minimum. A minimum will occur when you have a negative slope, a 0 slope, and then a positive slope. So we're looking for anywhere on this graph where we have negative y values, a 0 y value, and a positive y value. The only case is right there, negative y, 0, positive. So in the interior, the only possibility for a minimum would be here, but don't forget you have to consider the endpoints of the function. It's kind of a tricky little part. Okay, so g of 0 we found in part 1 is 3/2. G of -4, well, look at g. The area from -4 to -4 is 0. So, and this one, you don't really have to find g of 4. You did, right there, it's 11. But if these y values are positive, g is increasing from here on out. And so this couldn't possibly be a minimum. Okay, so then we have I'll just show you their answer. The g of -4 was 0. The g of 0 is 3/2, the only two places where we could have a minimum. And so then we write out the solution right here. Justify with work everything that you've done here. Okay, and then part C, find all intervals in which the graph is concave down. So that must be, we're thinking about the second derivative of g, which must be the derivative of f. And we're looking for negative parts, negative slopes for f. Okay, so from here all the way through to there, that slope is negative. Here to here negative, here to here negative. And let's look at their answer. Kind of a quick part of this problem. Concave down on that first, second, and third integral because g prime of x equals f of x, which is decreasing on these intervals. So just do your best to explain. I'm sure a calculus teacher would understand your explanation.